Before we actually move into the lesson on circular functions, I wanted to call your attention to these two equations. They're actually listed in your textbook. And the reason is because it demonstrates some non-geometric uses of trig. So far we've really just looked at triangles and we're sort of moving into circles, but there are some ways that trig actually represents real-life things occurring. So for example, this first equation here actually describes the shape of an ocean wave. The height is y, and the horizontal distance is x in meters. This second equation is actually the line of voltage of alternating current with time t listed in seconds. What you should recognize is that neither one of these actually uses angles. The variable here is a value that is not an angular measure. And that's actually how we're going to proceed today, is to look at these trig functions, but not as they relate to angles, but instead as they relate to two numbers. To develop these definitions, we are going to let this circle be a unit circle. Unit circle means that the radius of the circle is exactly 1 unit long, and this unit circle is centered about the origin. The equation is shown up here. What we'll do is we will start at point A, and we will travel some distance around, some arc length around, which we call S, over here to point P. The x and y coordinates of point P are going to be the cosine and the sine of this arc length S. Remember, this is 1. Here we've got a right triangle. So the sine of my angle is this y distance over 1, and the cosine will be this x distance over 1. Therefore, the sine of this arc is the y coordinate, and the cosine of the arc length will be the x coordinate. From here, we can use the reciprocal identities as well as quotient identities to determine the other 4 trig ratios. The only thing that you have to be aware of is that anything in the denominator cannot be equal to 0. Here are the rest of those functions. So if sine is y, the cosecant would be 1 over sine, or we could say 1 over y as long as y is not equal to 0. If the cosine is x, then the secant would be 1 over the cosine, or 1 over x, as long as x is not equal to 0. Sorry, that should have a 0 on it. Same thing with tangent and cotangent. That's why these reciprocal identities and the quotient identities are important. They will continue to show up. So from here, we'll try an example. We've got some number s. The point P is given, and it's s units from A, which is 1, 0 along a unit circle. Find the exact values of the 6 circular functions of s. You actually don't have to draw this picture. Remember, we know that the sine of s is the y value, so that's 4/5. And the cosine of s is the x value, so that's negative 3/5. We have reciprocal identities, so the cosecant of s will simply be the reciprocal, 5/4, and the secant of s will be the reciprocal of cosine, so negative 5/3. And then the last part, the tangent. Remember that tangent is really the sine over the cosine. So that would be 4/5 divided by negative 3/5. So we can copy, dot, flop, and that would give us negative 4/3. And then the cotangent would be the reciprocal. This next problem is almost ridiculously easy, but something that I want you to pay attention to. This is not given in degrees, so your calculator must be in radians. When I enter the sine of 1.16 in my calculator in radians, I will find that this is equal to 0.9168. Remember, if that degree sign is not there, then you must put this in radians. For this next problem, it would be very simple to just plunk this into the calculator in radian mode. But in the last class, we talked about some conversions that we should be familiar with. And one of them is that pi over 4 radians is equal to 45 degrees. And with 45 degrees, remember, we can rationalize from that right triangle. So the sine of pi over 4 will be opposite over hypotenuse. I'm referencing this angle, although it doesn't really matter. And so that's the square root of 2 over 2. The cosine of pi over 4 would also be square root of 2 over 2. And the tangent of pi over 4 would be 1. For this next example, again, you are given a clue that this needs to be in radians, and here's your clue. You'll find the cosine of x, not theta, right? It isn't going to be an angle, it's going to be x, a distance, but x has to be between 0 and pi over 2, so that tells me that my calculator must be in radians. And what I will do is take the inverse cosine of the value I'm given to calculate the value of x. So nothing in our procedure has changed except the fact that our calculator is now in a different mode. And I find that x is equal to 1.020. So if you remember, we said that we started with this equation, x squared plus y squared equal to 1. And that was the equation of our circle. Now remember, we said that the cosine of s was equal to x, and we said that the sine of s was equal to y. So we can, of course, substitute cosine s in for x, sine of s in for y. And this becomes one of our Pythagorean identities. This is one of the reasons that the Pythagorean identities work. For the rest of what we do, we will follow the practice of using circular functions as our trig functions. You'll know whether or not we're looking for measurements, distances versus angles by the context that we're using. If you see a variable like x or y we're using numbers, whereas if you see something like theta or alpha or beta or gamma, those will be referred to angles.